During our lecture, we discussed that mixture models are very flexible and can capture different shapes for the density of data. Now I want to illustrate that using 3 different examples. In the first example, I will show you how mixture models can capture multimodal distributions. And in particular, in this case, we will discuss a bimodal distribution. We're going to consider a mixture of 2 normals. This is our first example. We are going to plot a mixture of 2 components. The first component has a weight of 0.06. Obviously, the second component needs to have a weight equal to 1 minus that, so it's 0.4. And it's a mixture of 2 normals. The first normal is going to have a 0 mean and a standard deviation of 1. And the second component is going to have a mean of 5 and a standard deviation of 2. And what this code will do is it will provide us with a graph of the density associated with this mixture of 2 normal distributions. So the first thing that we do is we create a grid of values, in this case 100 values in between -5 and 12, on which we're going to compute the value of the density. This second line of code computes what the density is at each one of these x values. And if you remember from your R lessons, the function dnorm just computes the density of a normal distribution with mean, in this case, 0 and standard deviation 1 at a set of values given by the x value. The other 2 lines of code here just create the plot of the density. The first one just plays around with the margins. This is something very common, just to make the figure as square as possible. And this second line actually creates the plot. So let's execute these commands. We can see on the right-hand panel down here that now we have the density of that mixture of 2 normals. The value of the density is in the y-axis. The value of x is in the x-axis. And you can see that we have obtained 2 modes or 2 peaks in this distribution. And that is because the means of the 2 distributions are pretty far away. So one of them is 0, the other one is 5. And when compared with the standard deviation, so this has a standard deviation of only 1, and this has a standard deviation of only 2. So when you have mixtures, in this case of normals, where the means are very far away when you compare them with the standard deviations, then you will obtain distributions that are multimodal. If I were to have a third component in this mixture, then again, I were to pick values for the mean and the standard deviation that allow the peaks to be well separated, then I would see, for example, an extra peak somewhere down here. So in that regard, the mixture of normals allows you to capture multimodality in the data if it is present. Another example that is interesting is to show how a mixture of normals can capture skewed distributions. And if you remember, skewed distributions are distributions where one tail seems to taper out more slowly than the other tail. So to illustrate that, again, we're going to look at a mixture of 2 normals. We're going to look at the same x region that we had here. So we're still going to plot the density between -5 and 12. What changes now, it's both the weights and the means of the distributions that are involved in the mixture. The first weight in this case is, instead of 0.6, we're going to use a weight of 0.55, with the weight of the other component being 0.45. And then my components are going to have, the first one has mean 0 and a standard deviation of a square root of 2. And my second component is going to have a mean of 3 with a standard deviation of 4. You can see that now both the means are closer to each other. Instead of being 0 and 5, they are 0 and 3. And I'm using much larger standard deviations for each one of the components. So instead of 1, we're using a square root of 2, and instead of 2, we're using 4. So if we go ahead and again create a plot, you can see that now the two peaks are not distinguishable. And again, that's because the modes of the two normals, the means of the two normals, are much closer to each other than they were before, especially when you compare them against the standard deviations of the distributions. And you can see that the right tail in this case tapers off much more slowly, or so appears in the graph, than the tail of on the left-hand side. So this is an example of how a mixture of normals can give you a skewed distribution for your data. Finally, I want to illustrate one last property, and it's that mixture of normals can give you heavy tail distributions, or things that resemble heavy tail distributions. The example here, it's going to involve, instead of a mixture of two normals, is going to involve a mixture of three normals with weights 0.4, 0.4, and 0.2. We're going to plot it now over a slightly wider region. My region is going to go between -12 and 12. All three mixtures have the same, or all three components of the mixture have the same mean, 0, 0, and 0. What changes across the different components is the standard deviation associated with each one of them. So the standard deviation for the first one is the square root of 2. The standard deviation for the second one is the square root of 16. I could have just written 4 in there, but I wanted to kind of keep the pattern. And finally, a square root of 20 is the standard deviation for the last component in the mixture. In this case, I want to try to compare, so to illustrate the fact that we're getting heavy tails, I want to try to compare the plot of this density with the plot of the density of a normal distribution that has 0 mean, which is going to be the mean of this mixture. Remember the formulas that we discussed in the lecture. And that has a standard deviation that is the same standard deviation that the mixture. So in other words, I'm making this normal density have the first two moments be the same as the first two moments of the mixture of three normals that I have above. And that will allow me to make a fair comparison of how the tails look like. So I match the first two moments, and then given that I have matched the first two moments, I want to see how different the tails of the two distributions are. So let's go ahead and plot it. Again, we compute the three values, and then we plot both sets of graphs. And I'm also going to add a little legend that tells me which graph corresponds to the mixture and which graph corresponds to the Gaussian distribution. This is how the result looks like. The mixture model is drawn in a thick solid line, whereas the Gaussian distribution, the single Gaussian, is drawn on the dash, using the dashed line. And again, you can see how things are very different. Even though I have the same mean and the same standard deviation for both distributions, you can see that the solid line tends to fall more slowly once I get to high values, whereas the Gaussian distribution tends to fall faster. So this is what we call heavier tails. So at least for the purpose of the range in which I'm plotting, it would seem like the graph with the solid line tends to be above the graph for the dashed lines for either very small values or for very large values of the variable x. So this illustrates how this mixture of three normals is still symmetric. That's very important to highlight. This is a symmetric distribution just like the Gaussian, because the means are the same for all the components. They have the same variance, but the mixture has a much heavier tails.